In this video, we're going to discuss how we can perform a randomized complete block design with two blocking factors instead of just one. This type of design is called a Latin squares design. We'll discuss some extensions, how we can go even further later on. And the Latin squares design has a really interesting place in the design of experiments. It is a very particular design. I'm not going to say it's not useful. I think it's very useful, but it's useful when it's useful, just like all of the other designs that we're going to look at. Now, the Latin squares design, again, I find to be pretty useful in certain situations, and we'll talk about those in a bit. I will say that the reason I'm mentioning this is your textbook doesn't seem to think it's as useful as I do. But it really depends on the case that you're approaching, and we'll discuss that in just a bit. So for the text reference, this is going to be section 4.2 on page 153. So we're going to simultaneously control or eliminate two sources of nuisance variation. And again, one of the important things to consider here is that we're talking about two blocking factors, not necessarily just two independent variables. We do a different design for two independent variables. For Latin squares, this is for two blocking factors specifically. An important assumption, just like one of our main assumptions when we were looking at the blocking factor in the randomized complete block design, is that there's no interaction between the blocking factor and the independent variable. Here, an important assumption is that the three factors, the treatment and the two nuisance factors, don't interact with each other. The nuisance factors shouldn't interact with each other, the treatment shouldn't interact with either of them, and there should be no three-way interactions. It's bad to violate these results. So just like with the randomized complete block design, having an interaction can create some problems. Here, if we have an interaction with the Latin squares design, we can still have problems just like before. And again, when these are appropriate, these can be extremely useful in our data analysis situation, allowing us merely by a design component to be able to take into account a second source of variation. Again, a very useful trick to know. So in this particular case, we're wanting to test, so this is our first example, wanting to test different formulations of rocket propellant on the burn rate. Now, there's a couple things that we want to account for. We want to be able to look at the mixing strategies, so that's what we're really looking at. But we want to be able to account for the different raw material, the different batches that our mix came from, and we want to be able to account for who was doing the mixing in this particular case, so the operator. In this case, you can see how both batch and operator are two factors that we wish to control for. We literally don't care about batch or operator. Those aren't of interest to us. We just want to be able to control for these. And again, we can't randomly assign an observation within an operator to a different operator per se, nor can we randomly assign something that comes from the first batch to a second batch. That's not really an option. Now consider that this type of idea that we might have different batches of raw material and different operators is rather common. This, again, the book talks a bit about this in the opposite direction, but I find this to be a very feasible and plausible scenario, something that could very commonly happen. Maybe not as often, certainly not as often as the randomized complete block design example, but definitely something that can come up. Note that the structure of this particular design, how it's laid out right now, this structure shows three variables. So previously, when we looked at a table kind of like this, we were looking at two variables. Each of the rows represented the levels of a variable, in this case batches of raw material, and each of the columns represented levels of a variable. That would be the operator. But in this case, we actually have a third variable hidden inside of this table, and that comes from these letters. The letters are actually representing the different mix. So in this particular case, the letters represent a third variable. So in this table, though it's only a two-dimensional table, you can see how this is actually represented in 3 dimensions through the use of letters. So this is a 5 by 5 Latin squares design. We're always going to have the same number of rows and columns. That's where the word square comes from. Incidentally, these Latin letters are where the word Latin comes from. So that's how we come up with Latin square. Page 164 in your book shows some other Latin squares. In fact, your textbook talks about some fun details. It looks like on page 168. There's some cool details about the number of Latin squares possible. How many Latin squares can you make? We'll discuss that either later in this video or in the next video, depending on what we have time for. But check out that table in your textbook. I think it had some really fascinating statistics, at least for me, on the nature of Latin squares and how many we have. I found that information to be surprising the first time I was able to see that. So in general, looking at the Latin square design, we require the same number of factors for each of the variables. Now we said, hey, we're going to have the same number of rows and the same number of columns. What we're also saying here is if you look back, we do have the same number of rows and columns, but we also have the same number of levels in the variable that's being represented by A, B, C, D, E. So there's A, B, C, D, E. There are 5 levels of that variable. So not only do we need the same rows and the same columns, but we need the same A, B, C, D, E's such that we can represent those different variables. That means that there are P times P or P squared total runs in a Latin square design if we use P as the total number of factors levels in any given factor. And again, you can just think about that square. If I have P columns and P rows, there's going to be P times P or P squared total number of observations. Now note that in that previous design that comes out of the blocks, but there are also going to be P letters, treatments. And we also assume that each of the letters occurs only once within each row and column. So if we look back here, A, B, C, D, E, so each of those letters only occur once in the first column. A, B, C, D, E, each of the letters only occur once in the, first column in the first row. And you can do this with you can pick any of the rows and columns, and that should be the case, that this E should appear only once in the third row, and it should appear only once in the third column. So when you're thinking about this, think like a Sudoku puzzle, where you could only have a single number in any given row and column. That's a really good way to look at thinking about how those letters are going to occur. Now the rows and columns, those are pretty straightforward because that's what we've been doing before. But adding this letters component to add the third dimension, that is definitely a little different. All right, so for a couple examples of Latin squares, now we have a whole ton of different ways we can design these. Again, your book has a couple examples, and we'll talk about how to build them in R. But in the Latin square, we've got ABC, BCA, CAB. So on each of the rows and each of the columns, ABC, BCA, CAB, each of the rows and each of the columns, we only have one letter in each one. So this is a valid Latin squares design for a 3 by 3. In a 4 by 4, we have this other design. What I'll note here real quick is that these are our designs, and the 3 by 3 comes from how many rows do we have? 3 rows, 3 columns, so 3 by 3 Latin squares design, or Latin squares design dimension 3, because we know that it's going to be a square. But in this case, you're also involving 3 letters. So remember that in this case, though it's a table of 2 dimensions, this is actually 3 variables: the columns variable, the rows variable, and the letters variable. Now for the Latin squares design, we have something called a standard Latin squares. Now this standard Latin squares is just a Latin squares in which the first row and the first column are written alphabetically. So we could mix up the rows and columns here, but to create standard Latin squares, we would have the first column A, B, C be written in alphabetical order, and the first row A, B, C be written in alphabetical order. This is a standard Latin squares. Same thing with this 4 by 4, it's also a standard Latin squares. Depending on the size of P, there can be more than one standard Latin square. In fact, your textbook has some descriptions. Here are a couple fun ones for 2 and 3 treatments. So for P equals 2 and 3, 2 rows, 2 columns, 3 rows, 3 columns, there's only a single standard square that you can do. So in this 3 by 3, this is the only standard Latin square that we could have. We could have non-standard Latin squares, that's fine, where we mix it all up, but then the first row or the first column wouldn't be in alphabetical order. So if we put the first row and first column in alphabetical order, there's only one way that we could do this. For P equals 4, so let's say we have a 4 by 4, there are actually 4 standard squares that we could select. And as we go up, there become more and more. In fact, it kind of explodes. So with 5, there's 56 standard squares we can select. With 6, there's 9,408 standard squares we can select. And again, I encourage you to go check out your textbooks for some more of these statistics because I found them very, very interesting. But these, at least the ones reported on this slide, are specifically for the standard Latin squares. And again, a standard Latin square is where we write them in order. All right, so I said that there are 4 options for a 4 by 4 standard Latin squares design. You can go on and check them out here. Again, for all of these, each letter only occurs in each column and each row one time. Because these are standard, the first row and the first column are all going to be in alphabetical order, which is the definition of standard. So you can check that in all 4 of these, that's true. The first row and the first column read A, B, C, D. So I want you to consider, given that the first row and the first column are all the exact same in each one of these, that's the definition of the standard Latin square, they're in that particular row, what's actually changing? And if you take a second to look at this, you can even pause the video to try to think through this for a second. If you take a second to look at this, hopefully you see that these 3 values on the inside, this 3 by 3 subsquare, is actually where these different designs are getting manipulated and changed out. So there's a whole bunch of different ways that you can select what's going on in the middle here, given the limitation that the first row and the first column are all in alphabetical order. Now thinking about this, because we have 2 blocks, now we have 2 restrictions on randomization, and this is kind of weird. 2 restrictions on randomization. And this is coming from, again, each of our blocking factors represents a restriction on randomization. Consider the complications that arise when we have to do 2 restrictions. Consider how you would do this mentally. Actually, maybe it's worth pausing the video, thinking about for a minute or two, considering how you would do this mentally. Now, if you've come back and you don't have a good answer for how you would do that, I think that's absolutely legit. I don't know how I would do that if I hadn't studied this. That's something that's kind of complicated to think through. How would you randomize when both your rows and your columns seem to be fixed? And the key is going to come in when we look at those Latin letters and realize that we're actually counting for 3 variables instead of 2. If we just had the rows fixed and the columns fixed, there's not much that we can do. So in this case, we do have the rows fixed and the columns fixed. That is, that they're both representing restrictions on randomization, not that they're fixed level factors. But when we have restrictions on randomization for both the rows and the columns, that doesn't mean that the Latin letters are restricted. So that's where we're going to be incorporating some of this. So there are a variety of ways to work on this randomization in the Latin square. We're just going to talk about one of them that we're going to present, like how you would kind of do it by hand. But in R, there's definitely more ways that you could do this. So remember, in our goal, it's not necessarily about randomizing run order. Our goal is in randomizing the assignment. So remember, randomizing the run order, that's easy. Once I have different things set, I can just say, hey, this is going to go first, this is going to go second, this is going to go third. What's complicated here is that we have to randomize the assignment. How are we assigning these different treatments to these different block combinations when each of the block and each of their levels represent a restriction on randomization? So that's the complication. All right, so for our steps, this is how we're actually going to go through this. Step one, we're going to randomly select one of the standard squares, and we're going to play with p equals 4. It's small. It's small enough so that we don't have a ton of writing that we have to do with only a 4 by 4 matrix, but it's large enough that we don't just have a single standard square. So that's why we're using p equals 4. So we're going to randomly select one of the standard squares. Then we're going to randomly order all but the first row. So we don't need to worry about randomly ordering the first row. We're going to randomly order all the rows except for the first one. And then we're going to randomly order all the columns on that new matrix that we get after step 2. So pretty much we're just trying to do as many random steps as possible. So randomly selecting the first square, randomly ordering all but the first row, and then randomly ordering all the columns. That's the idea. So first, randomly selecting one of the standard squares. So we had the 4 to choose from previously. I'm just going to pretend that our standard square that we selected is this one, and I used a random number generator to pick 1 through 4. I assigned each of those 4 squares that we displayed on the previous slide a number between 1 and 4, and whatever the random number generator generated, that's what I'm going to use. So in this case, it generated this matrix, so this is the one that I'm going to start with. So now, step 2, I'm going to randomly order all but the first row. So let's think about this. I need to figure out which row it's coming from and which row it's going to. So the original row, I'm going to have the original rows of 2, 3, and 4, and then I'm going to figure out where is it going to where is this original row going. So row 2 is going to go to row 4, row 3 is going to go to row 2, and row 4 is going to go to row 3. All right, so here's my original. This is what I had on the previous slide. And now I'm going to apply this shuffle. So row 2, the BADC, is going to go to row 4, BADC. Row 3, this CDBA, is going to go to row 2, CDBA. And row 4, this DCAB, is going to go to row 3. So that's what's going on here when I'm randomizing all rows except for the first one. This is how we accomplish step 2. Now our final step is we randomly order all the columns including the first one. So we're going to randomly order all of our columns. So just like we had before, we're going to have our original, this is a typo, this should say column, excuse me. So we're going to have our original column, 1, 2, 3, and 4, and then we're going to shuffle it around. So column 1 is going to go to column 4, column 2 is going to go to column 2, column 3 is going to go to column 1, column 4 is going to go to column 3. Incidentally, if you're typing this in R, if you just do sample, open parentheses, 1 colon 4, close parentheses, that will give you this shuffle order from the numbers 1 to 4. So it'll actually sample all of those numbers and display them all in a random order. So in the previous slide, you could have done sample, open parentheses, 2 colon 4, and that would have sampled the numbers from 2 to 4 and put them in a random order. Here, I would do sample 1 to 4, and then the first number that I get, that's where the original column 1 would go to. The second number I get, that's where the original column 2 would go to, etc. Note that it doesn't have to be different. We can randomly select that the column stays put. So in this case, the second column is going to stay put, and that's okay because this is a random selection. In fact, even if every single thing stayed put, I'd want to double check my random generator to make sure that if I did it again, that wouldn't be identical. But even if everything stayed put, that'd be okay if I'm using my random generator. So I've got my random rows, and now I'm going to take the original column from column 1, and that's going to go to column 4. So the column beginning with A is going to jump into column 4. Column 2 is going to stay the same, so column B is going to stay right where it is in the second column. Column 3, C, is now going to go to the first column, and column 4, D, is now going to go to the third column. So that's going to be our random shuffle of columns. Now, here we have arrived at our randomized rows and columns. We're all set. So there's even more of these that you can do, these Latin square designs. They go on and on. So the concept of Latin squares we can absolutely extend. We've got the idea of a Greco-Latin square. So this Greco-Latin square adds in a Greek letter in addition to a Latin letter by doing some kind of transformation on the square that you have. So you come up with two squares that are orthogonal, and then you map them to each other, and you get this cool Greco-Latin square that allows you to account for 3 blocking factors. And the hyper Greco-Latin square allows you to account for 4 blocking factors, and you can keep going with this. It's very, very cool. So the reason that this is so cool, one of the most awesome things here, is that this is an extremely efficient use of data. We have p squared runs, and previously we were accounting for, let's see, in the randomized complete block design, we could use that many runs to account for 1 blocking factor. In the Latin squares, we can use p squared runs to account for 2 blocking factors. In the Greco-Latin squares, we can use p squared runs to account for 3 blocking factors. In the hyper Greco-Latin squares, we can use p squared runs to account for 4 blocking factors. So we are efficiently using data. We are using data so efficiently in this case because of the way in which our design is constructed. And also, what's kind of fun is that analytically, this is not difficult. I'll say that the first time I ever was exposed to the Latin square design, I thought because of how interesting and cool this design was that the analysis is going to be extremely complicated, and it's just not. It's not complicated at all. Specifically to run in R, it's going to be sleep through it, simple. But the design is another story, and this is a great case of why this course is not focused around the analysis, because the analysis is boring. But this design component, where I can take the same number of runs, and if I organize them in a very efficient and pre-planned way, can use them to account for more variables, many more variables than you would normally think is possible, you can actually analyze to test all of these different variables under some assumptions. Or you can analyze this data to test your treatment under a whole bunch of different blocking factors. So maybe we have the different raw materials and the different operators that we're talking about doing the different mixes in, but maybe they have to do the different mixes in different days. So we want to account for a 3rd blocking factor. You can do that using the same amount of experimental units using without having to increase your sample size. And this is a very, very, very cool thing. This is why I love the Latin squares in this concept of Greco and hyper Greco Latin squares. We're not going to go in depth on this in this class. This is definitely a next step. You're welcome to check this out. I think the textbook does have an example that you're welcome to go and see. I don't think the textbook goes into hyper Greco Latin squares, but feel free to go on and Google it if it's something you're interested in. But just the concept of Latin squares, that we can use this data to begin to account for multiple blocking factors and that we can extend this. Remember, it's not the analysis of the blocking factors that's important. It's how the blocking factors restrict randomization. And given that this blocking factor is supposed to restrict randomization, how can we possibly even accomplish that? That's the really cool thing going on here. It's not the analysis. This is the design. This is why we're in design of experiments, to talk about these really cool designs. In the next lecture, we'll talk about analyzing and replicating Latin squares, how we incorporate the Latin squares and the blocking factors into our ANOVA table, what this is going to look like, what replication inside of Latin squares looks like, how can that be done, can that be done, does that even make sense to do? We will talk about that all in the next video.